Alrighty, so up until this point, we've been looking at the outputs from our models line by line, looking at the results, the accuracy, the cost from each epoch of training. Now, looking at things like that visually, trying to see how our model is performing isn't the ideal way to do things. So the folks working on TensorFlow built this wonderful package called TensorBoard. So I'm going to show you now how to build TensorBoard into your Keras code, how to run it, and how to understand the outputs. So in the AlexNet in Keras notebook that I've already prepared for you, this is already done, but we're going to add it in to show how it's done. So after you've configured your model, we're going to add some new lines. You can press B to add a new line below, escape 4 to add a subtitle, and we're going to say configure TensorBoard here. We're going to shift enter to execute the cell, A to insert another cell above, and we're going to create a new variable here called TensorBoard, and it's going to instantiate a new TensorBoard object, which I have to add into our dependencies. So Keras callbacks import TensorBoard. There we go. Now we can instantiate the object down here. So this is pretty straightforward. All we need to do is specify where we would like to output our logs. So in my case here, I have a directory called logs. So these are all of the notebooks inside the notebooks directory that I created for you guys. And I made a directory here, logs, which you can make yourselves with make dir logs. And that's where I want to output the results. So after every epoch, Keras will write information into that logs file because we specified here, so logs directory, and then you want to create a name signifying the specific notebook or this specific run of this notebook. So I'm going to call it AlexNet. And then you run that line, and you simply fit your model just as before. So we're going to do the same thing in our VGGNet here. We're going to add in the same dependency at the top. So from Keras, callbacks, import TensorBoard, and same thing at the bottom. We're going to add a new line to instantiate an instance of TensorBoard. And we're going to give it a different name. So we're going to still put it in the logs directory, but we're going to call this one VGGNet so that we can distinguish our results from AlexNet and our results from VGGNet. And then same thing, we train the model as usual. So I've already done that. So I already have inside my logs here, I have two directories, AlexNet and VGGNet. I ran these overnight a number of days ago. So all the results are finished. You can have a look inside the directory, and you can see there's this event out file, and we have a similar kind of thing in the VGGNet file. It's the same kind of thing happening in here. So these log files can be read by TensorBoard so that we can see a beautiful visual output of our results from these two models. Now, to run TensorBoard itself, in a command line prompt, you type in TensorBoard, and you need to specify where the directory is. So that's log directory, and in my case, I put it in users, John, that's my name, and TensorFlow live lessons, notebooks, logs, And we also need to specify a port to output these results to. So we're going to run this TensorBoard on port 6006, which is the typical port that TensorBoard is run on. And we press enter to run this. We wait a few moments for it to do some calculations, and it says, okay, we've started TensorBoard on port 6006. So we can take this address that it spit out, and we can open a new tab in our browser, paste in the address with that port number, and voila, look at that, beautiful TensorBoard. So there are a few things that I want to show you in here. So to make things simple at first, let's only look at the results from one run. So you can see the names of the AlexNet and VGNet directories that we created here are individual runs that we can select. So this is why it's important to name your directories well, so you know what you're looking at here. So let's uncheck VGGNet so that we're only looking at AlexNet first. Now let's have a look at our accuracy and our loss. So these are both training results. So these are the results on the training set. Our accuracy went up over time. If we hover over the chart, we can see detailed statistics. So you can see the time of day that this happened at. You can see specifically what step or epoch this was. Step and epoch are used as synonyms in this instance. And so we ran 100 epochs, and we can see that in the 100th epoch, we had our highest accuracy. So it was 86. I can't both show you with my mouse, but hopefully you can see just below the value label there, we had 86.2% accuracy in the 99 in step 99, which is the 100th epoch, and that took 52 minutes and 20 seconds to run. So at the same time, our loss, our cost, went down, which is unsurprising. So the cost is what we were trying to minimize with our stochastic gradient descent over all of these epochs. And as a net effect of that, our classification accuracy went up over time. Now, until a point where we received more than 80%, 86% accuracy on categorizing the 17 classes of Oxford flower images. Now, that's just our training accuracy. The results on our validation set aren't quite as good. So the first thing to notice is you can see in the background there is a lot more variability in the validation accuracy. And that's partly to do with it being a smaller data set. But you'll also notice that the validation accuracy is lower. So at its peak, we had, at the very end here, in step 99, which is the 100th epoch, we had 63% validation accuracy. Now, it looks like, and this is the kind of thing that you can see really nicely in this TensorBoard output. It would have been difficult to visualize this just by looking at the numbers in our Jupyter notebook. But it looks like our validation accuracy took a turn for the better just at the end of our training. So we might have stopped training too early. It seems like it would be wise to increase our number of epochs to 200 and run this neural network again to see how our results pan out. So this is looking at things from the step perspective. You can zoom in on any points here by creating a box. So it's pretty cool. You can really get a detailed view of things. You can change the smoothing. So there's this overlain dark orange line. So that's actually computed in TensorBoard itself. So we can reduce our smoothing. If we reduce it down to 0, then all we're seeing is the raw output. If we increase our smoothing to 1, then we get an even smoother line over top of the raw output. So let's put that back around here so we can see the overall trend pretty well, around 0.6, 0.7. And then we have some other views here. So instead of looking at it just step by step, we can also click on wall here And we can actually see the compute in real time. So I ran this on May 27th, and it ran from 6:30 through to 7:30. Now, let's see how that compares with VGGNet. So now look at that. Our VGGNet, which you may recall is deeper than AlexNet, which has an order of magnitude more parameters to fit than AlexNet, it took a lot longer to run. And in the end, its results weren't even as good. So from an accuracy or a validation accuracy perspective, the shallower AlexNet greatly outperformed VGGNet. So either we were using too deep of a network for VGGNet, or we didn't have our hyperparameters tuned appropriately, or maybe the Oxford 17 flowers dataset was just too simple for the VGGNet, and so the AlexNet was simply better suited to that task. If we look at this over steps, it doesn't look as dramatic because we ran VGGNet for 250 steps, whereas AlexNet was just 100. But nevertheless, you can still see the outperformance from AlexNet here. Now, interestingly, with AlexNet, it looked like we should have been running it longer because our validation accuracy was just reaching a peak when we cut it off. But with VGGNet, it doesn't really look like things were going to get any better. So with VGGNet, from the, what epoch is this here? From the 118th epoch here, our accuracy goes down and then it catches back up again. But our validation accuracy really plateaus. So what's happening here is our accuracy continues to climb. We're overfitting on the training data, but the validation data isn't moving anywhere. So while the AlexNet could probably have been trained longer, it looks like we trained our VGGNet too long and could have stopped early, maybe back here around the 115th step. So we have a couple other views to quickly explore here. We can pop into graphs here, and this is showing a detailed view of our AlexNet structure. So you can zoom in on it, and this shows all of the individual operations that are happening. So the lines represent data, or tensors, we can call these lines, in between nodes, and in each of these nodes, operations are happening. So keep that terminology in mind. Up next, we're going to explore TensorFlow proper, and we're going to start thinking about building our artificial neural networks with this kind of terminology, with tensors of data passing in between operations where those data are transformed and output into further operations.